All right, solar flares, which are part of the chromosphere. What will happen is between these sunspots, the gas trapped up here, for some reason right in here, a solar flare occurs. In between it. So in this case, this is the flare right here. These are actually sunspots. This is taken in a weird light, so it looks kind of weird. But there's a real brightening, there's a real bright spot that all of a sudden occurs on the sun. Lasts for about 10 to 20 minutes. Okay? At that time that occurs, it starts pushing the magnetic field upward. And so it pushes the magnetic field out. And what we're really seeing is kind of an eruption here. The magnetic field starts to get bigger, and then the magnetic field starts to get bigger, and then eventually the magnetic field just breaks. Or you can imagine like this, if my fingers are in the magnetic field, if I'm holding it like this, but somebody's pushing up on it, I can stretch, but eventually my hands fly apart. That's what happens here too. Is the magnetic field's like this, and then boom, it flies apart. That happens in a solar flare. And when that solar flare occurs, what happens to all this gas? Well, all this gas gets ejected out into space and comes flying out towards the solar system. Yeah. And it becomes part of what we call a CME, which stands for a coronal mass ejection. And they're all tied together here. I'll come back to that more in a second, what that really means. But this is what solar flares, and so from the Earth, a solar flare is actually this brightening, this really bright spot that all of a sudden shows up. Notice this was in July 2000. This was right near sunspot maximum. And all these little parts here are actually sunspots. This is an ultraviolet picture, which is why it looks kind of weird colored and everything. But all that energy, these are all sunspot groups, that's where all the energy is. So solar flares are also, everything seems to be tied to these sunspots. All the activity on the sun. These are all prominences. You see all the gas trapped up in there? And so there's all kinds of, this is super active sun. And those solar flares, we see and they last for 10 to 15 minutes. Now these particles that get launched out from the flare, here's one here, it's a smaller one, but there's a brightening right there, occurs, and it takes about 2 days for those particles to reach the Earth. Well, when those particles reach the Earth, they interact with our atmosphere. So what happens up here, here's the sun, and it has a flare, and all those particles come flying out through the solar system. Well, then they hit the Earth over here, but the Earth has its own magnetic field. Now our magnetic field actually is stretched out behind us because the sun pushes it that way. But what happens to the particles when they hit the Earth's magnetic field, they get pushed around to the poles because of the magnetic field of the Earth, and they start to come around and then they fall into our atmosphere. They get pushed in the atmosphere. Well, when the particles hit the atmosphere, they excite the atmosphere. All the gases in our atmosphere get excited and they glow, and we create aurora, or what we call the northern lights, or the technical name is aurora borealis. And at the same time, it's going to happen in the southern hemisphere, so you have the southern lights. Or aurora, which is what light is, aurora australis. Because Australia just means south. Yeah? In fact, that's why Australia was named for it was the southern continent. So, all these particles coming from the sun get funneled into the Earth, and we see this as auroras, or northern lights. If you haven't ever seen them, you should go see them because they're very cool. When you look up in the sky and you see the sky glowing different colors, they can be green, they can be red. The color depends on what gases are being excited in the atmosphere. And it varies depending on how energetic the particles are coming in, how far down it is, what latitude it is. Now, if there's especially massive coronal mass ejection where all this material can fly out, it starts to squeeze further and further to smaller latitudes, and it is even possible that you can get particles that come far enough that even in our low latitude, like Texas, you can get northern lights here, or aurora borealis. It doesn't happen very often. But if you live in like Alaska, you see it all the time. In fact, you see it even in sunspot minimum. There's a flow coming from the sun, and you see them all the time. In fact, they say 2 out of 3 nights you see them in Alaska. The more active the sun is, the more it pushes to smaller or lower latitudes. Here is one which is kind of cool because it has a combination of different colors. It has red and blue. This happens to be in Colorado. I know that because you see this right here. This is the constellation Cassiopeia, and it's going to point towards the North Star up here, and the North Star being that high gives you a rough idea what your latitude is. See how everything ties together in astronomy? But that is the northern lights over the tops of the mountains. Here's a picture I took. I went to Fairbanks, Alaska a few years ago, and one of the reasons I went was because I wanted to see the aurora. I had seen them before because I grew up in Montana, and in Montana we would occasionally see them near sunspot maximum. I had seen them before. I'd seen red ones, mostly red, but then I saw these green ones. These were beautiful. They tend to move around, and they can be like curtains, kind of shimmery, and the space station sees them from space looking down on it, which is also a cool way to see it. And they're brighter than you think. So when you get a chance, plan on going and see the aurora sometime in your life. Put it on your bucket list so you can do that. And the best time is to do it near sunspot maximum because it's much more active. So 2024, just a few years from now, plan on going to Canada, Alaska, Norway, somewhere far north or somewhere very far south. There's not as much landmass far south, so it's harder to see them. But do that as one of your things to do sometime in your life. All right. Now, third part of the atmosphere. So I'm going over here, number 3. So I'm still on my sun's atmosphere. This is the third one. 2. This is 3. The third part is the corona, which we mentioned when we talked about eclipses because it really only shows up when you block out the photosphere. Because the photosphere is producing so many photons you can't see this otherwise. The corona is several million degrees Kelvin. So very hot. Very, very hot. And it's very, very hot because these particles are getting energy from all the magnetic field activity around the sun. Okay? Now, even though there's several million degrees, you can fly right through the corona. It's very low density. There's not many atoms per volume. And so you can fly right through. We've had spacecraft that have flown through it. Comets go right through the corona. Doesn't stop it. Okay? So these particles are very, very thin, but each particle has a lot of energy. And the corona tends to change shape. If we're near sunspot minimum, then the corona makes this nice, perfect circle around the sun, which is where the term came from. It's called, corona means crown, so that would be the crown of the sun. And you could see it only when it eclipsed, blocked out the sun, then you would see this glowing sphere around it. But when the sun is very active, the corona changes shapes. And this is a very active sun, and you see, you get things like streamers, these are called, and you get holes, blank spots here. So we can see coronal holes. And the particles that make up the corona, we're not sure, but they seem to be associated with these prominences and stuff. Essentially, the particles get very hot, and then if the sun is very low active, not very active, all those hot particles tend to just make a nice uniform circle. But when you have all these solar flares going off, the flares are blasting holes through it. They're actually creating more particles, but they're blasting holes through it, creating what they call CMEs, which means coronal mass ejection. You're actually blowing the corona away, and that's what the particles that fly out to the Earth and hit us. And they hit all the solar system, not just us. So all this is tied together. When we're at sunspot minimum, you get a nice perfectly round corona. When you're near sunspot max, you get coronas that look like this. And that's why astronomers love eclipses when it's near a sunspot maximum, because the corona is a lot cooler to look at than just a nice perfectly round. Which is good, because 2024, when the next solar eclipse comes right through Dallas and right through Texas here, is also near sunspot maximum. And so we should have a very cool looking corona at that time. All right, here's more pictures of the corona. This is an X-ray picture showing that the gas, the hot glowing gas, seems to be associated around sunspot period. This was during sunspot maximum. This is 2003. So the sun was very active. And so the particles seem to be coming from these active regions, these very hot regions, but they also get disrupted by the events going on, the solar flares and the other material going on the sun. All right, this is not a very good picture. It's supposed to show the rotation of the sun, but we'll talk about that next. All right, so those are the layers in the activity going on in the sun. So remember, just quick review, for the interior of the sun we have three parts. We have the core, we have the radiated zone, we have the convective zone. But the atmosphere also has three parts. In the atmosphere we have three parts. We have the photosphere, we have the chromosphere, and we have the corona. And within each of these layers you see different effects. You see granulation in sunspots here, you see prominences and flares here, and you see coronal holes in the third one. All right, why is the sun have this 11-year cycle, and what makes all this work? Well, really it comes down to the rotation of the sun. So here's the sun with its north pole and south pole. It rotates counterclockwise just like everything else in the solar system. However, unlike the Earth, it takes about 25 days for the equator to rotate around once. But as you get further out, it takes longer. 27 days, 29 days. And so the further you get from the equator of the sun, the slower it's rotating.